I'm Dr. Chris Creighton, and we're going to be continuing to discuss logarithmic and exponential equations, this time with compound interest. The core goal here is continuing to solve exponential and logarithmic equations. In particular, we're adding in some modeling. So, solving this logarithmic equation, the first thing we know is that we have log base 2 of x plus log base 2 of x minus 7 is equal to 3. So, when you're solving logarithms, your core goal here is to get all the logarithms on each side grouped into a singular logarithm. So in this case here, I'm going to group these two together. So I'm going to get log base 2 of x times an x minus 7 is equal to 3. That's because if you have the two logarithms adding, the insides multiply. The one additional thing I want to notice here is that we have a domain change. That domain change, in this case here, when you combine this particular combination, adds solutions, which is okay. It's okay that we can add solutions. Like radical equations, we can add solutions. Doing this can add solutions. If you pulled this apart more, can't really do that. But if you did, you would lose solutions, so just be careful. You want to combine things. So in this case here, then we convert it to exponential form. So we get x squared minus 7x. So I'm going to multiply that inside there. And then I get 2 cubed, which is equal to 8. So this turns into the polynomial x squared minus 7x minus 8 is equal to 0. And then we come back down to factoring. So this thing then factors as an x minus 8 times an x plus 1 is equal to 0. So x is equal to 8 or x is equal to minus 1. So again, going back to potentially adding solutions, we absolutely always have to check our answers. So checking these, so x is equal to 8, we get log base 2 of 8 plus log base 2 of an 8 minus a 7. That's equal to log base 2 of an 8 plus log base 2 of 1. That's equal to 3 plus 0, which is equal to 3. So that works out great. Checking the other one, the minus 1, we get log base 2 of minus 1 plus log base 2 of a minus 1 minus 7. Now, this is not defined, so this is not a solution. This is not in the domain of the logarithm. So in this case here, x is not negative 1. We get our singular solution as x is equal to 8. That negative 1 came about from the fact that when we combine these two logarithms, it changed the domain of the function, which added in this additional solution. You absolutely have to check all of your answers. All right, so for our next one, we're going to solve log base 3 of 3x plus 2 minus log base 3 of x is equal to log base 3 of 4. So again, the first thing I see is that we should combine the two logarithms on the left side to equal a single logarithm. Now they're subtracted, so that turns into division. So in this case here, we get log base 3 of a 3x plus 2 divided by an x. And that's going to be log base 3 of 4. So again, word of warning, this added solutions. So we still have to check. Now, as log base 3 of x and log base, any valid base of x, are one-to-one functions, we get the fact that 3x plus 2 divided by x is equal to 4. This one comes because log base 3 of x is 1, 2, 1. All right? Because the values of the logarithms are equal, the inputs of the logarithms have to be equal. And that puts us down to this little bit of an annoying rational function. But that's okay. The first thing I see here is I see an x in the denominator. Do not want an x in the denominator. So what I'm going to do is multiply both sides by an x. That turns into this, on the left-hand side, an x divided by an x. So that turns into 1. So that's equal to 3x plus 2 is equal to 4x. Subtracting 4x from both sides, or 3 from both sides, we get x is equal to 2. Now, we could have added a solution. This may have no solutions at all. So we have to check. So checking this, we get x is equal to 2. log base 3 of 3 times 2 plus 2 minus log base 3 of 2. And so what we should be getting is a log base 3 of 4. So this equals log base 3, 6, again 8, minus log base 3 of 2, which now we can combine our logarithms to get log base 3 of an 8 over 2. You can only combine logarithms when the values on the insides are positive. So in this case here, that's equal to log base 3 of 4, which works out great. So that is, in fact, our nice little solution there. So as an application of exponential and logarithmic equations, there comes this idea with compound interest. Actually, compound interest started way before. So it's essentially the idea of, okay, you deposit money into an account. That account accumulates interest. Then it accumulates interest on the new amount, which is essentially accumulating interest on interest. So it's compounding the interest. So there's two versions of compound interest. There's the finite version and there's the continuous version. So for the finite version, we have the formula A is equal to P 1 plus R over N to the NT. So explaining this a little bit, this is your principal, which is your initial deposit. You have your value n here. N, this one corresponds to the finite. This is n is equal to the number of times compounded per period t. So t here is like period. So like in this case here, this is time. So like for instance here, if we want to say this thing is compounded monthly for 1 year, t would be 1, n would be 12. And that leaves the r. So r here is our interest rate. And I want to point out you need to write this as a decimal. Often they'll give it to you as a percent. You need to divide it by 100. So knowing all of these values, the principal, your interest rate, the number of times it's compounding, for instance, a credit card would be monthly, so that'd be 12, and how long you're compounding for, so t, you can find about the amount in the account. So that's the finite version. The finite version, the difference between finite and continuous version is that there's a finite number of times it's compounded per period. The continuous version is A is equal to P e to the RT, where in this case here, A is still the amount in the account, P is still the principal, R is still the interest rate, and T is still time period. So the difference between finite and continuous is typically the words. You're going to see something over here like compounded monthly. So like that's like n is equal to 12. And over here you'll see something like compounded continuously. Then you'll use this formula. So if you see the word continuous and the word compound, it's the continuous formula. If you see the words compounded and you see some period like monthly or quarterly, so you get like by 4s, then you use the finite version. So in this example here, let's say we're depositing $1,500 into account at 3.5% interest compounded monthly. So this one is going to be the finite compounded interest formula. And so we want to know how much is in the account in 3 years. So in this case here, we know that the principal here is going to be $1,500. You're going to deposit $1,500. Say like you're saving up for like a trip or something. Your interest rate, R, is going to be 0.035. It converts to it as a decimal. You divide that percent by 100. Monthly, compounded monthly, again, this tells us we're going to be using the finite version, tells us that here that n is equal to 12. So those are our base values. Then coming down to part A here, how much is the account in 3 years? T is equal to 3. So using our formula, A is equal to P1 plus R over N to the NT. And then plugging in all these values, we get 1,500, 1 plus 0.035 divided by 12 to the 12 times 3 power. And then punching that into my calculator, so I get 1,500 times 1 plus 0.035 divided by 12, all to the 12 times 3. I get $16.65 and 81 cents in the account after 3 years. Now that's a little bit of low interest rate. You may have been like, hey, it's been 3 years. I would expect more. But not so much of a 3.5% interest rate, and particularly you only deposited $1,500 in there. So this is a reasonable amount of growth. So then it leads us to the second question: how long does it take to double? So you deposit $1,500 in the account, don't touch it, and you're like, hey, my trip costs $3,000. How much does it take? So in this case here, the doubling time, this one will amount to having your the amount you want in the account, A, is equal to twice your principal. So you can actually tell your doubling time if you don't know what your principal is, because it's just twice P. So in this case here, though, we do know that P is 1,500, so that is equal to 3,000. So in this case here, we get 3,000 is equal to 1,500, going by the formula right above, 1 plus 0.035 divided by 12 to the 12 times t. And this is what we want to find. How long does it take? We want to get that t. This gets a little bit annoying. So then, dividing by 1,500, I get 2 is equal to 1 plus 0.035 over 12 to the 12t. And then you go, hey, what we want here is in the exponent, so I need to take a logarithm. So taking a log of both sides, one that we can value, I'm going to use the natural log. We get log of 2 is equal to 12t log of this pretty annoying looking thing. So then t is equal to log of 2 divided by 12 log of 1 plus 0.035 over 12. And then punching that in my calculator, so log of 2 divided by 12 log of 1 plus 0.035 divided by 12, I get that this is going to double in 19 years, 0.83. It's like almost 20 years. It's going to take forever for this thing to double. So, think about this though. You deposited $1,500 into the account, and it just sits there at this constant interest rate. It'll generate 3.5% per month, or compounded monthly, which isn't a whole lot of money. So this thing is going to take forever to do it. That's why typically when you are trying to save something, you're going to want to tuck away a bit of money each month, because then this thing will compound interest, and you deposit some more, and then the interest will just start building up on itself.